So we are moving on to our first ALEKS assignment. So let me pull that screen over. Not that one. Hopefully, most of this module you have passed off in your knowledge check. Some of it you probably won't have. But this first module, I don't know why, but in education we quit calling them chapters or units, and now we call them modules. I don't know. Arose by any other name, right? So there are like 24 topics in this module, and it's just sort of a review chapter. So I'm going to spend a couple days going through the different types of problems, and then you guys can pass them off. So we won't have a test in this module. We're just going to pass off the topics, and then we'll move on to module 2. All right? So we start off. Let's do it this way. Acute, obtuse, and right. What does it mean to be an acute triangle, an acute angle? Less than 90. It's a cute little angle. C would be an acute angle at 75. Right angles are obviously 90 degrees. Obtuse angles would be bigger than 90. Yeah. They're obese angles. The obese angles. I've never heard that one. So, okay. That one's easy. Finding the x and y intercepts. The y-intercept here would be 4. The x-intercept is going to be 2. Easy enough. Oh, -4. You're right. So the measure of angle 2 is 32 degrees. Find the measure of angle 1. 1 and 2 form a straight line. So they add to be 180 degrees. We would take 180 and subtract 32, and we get 148. What do we call two angles that add up to be 180? Starts with an S. Not symmetrical. Symmetrical is not a word. Symmetric. People disagree with me, but I'll fight them. Symmetric is the word. Symmetric. Yeah, well, when I fight them, it'll be dirty. Like, they won't see it coming. Maybe I shouldn't record this and put it on the internet. So what is it called when two angles add up to 180? It is a straight line, but there's a word for it. Not symmetrical. Supplementary. Supplementary means two angles that add up to be 180. What do we call it when two angles add up to 90? Starts with a C. Complementary. Supplementary means 180. Complementary means 90. What angle would be complementary to angle 2? How big would the angle have to? So angle 2 is less than 90. So how big would an angle need to be in order to be complementary to angle 2? It would be. How big, though? What's 90 minus 32? Exactly. Nope, that's supplementary. So, right? So 180 minus 32 is 148. So not 68, 58. 58. Yep. So an angle that is supplementary to angle 2 would be 148 because they add to 180. An angle that is complementary to angle 2 would be 58 because they add up to 90. Yeah. The mic doesn't pick you guys up very well. Yeah, it picks up my voice, but not yours. So, and in this topic, it wants you to do segment addition. So if segment PQ is 9 and segment PR is 11, how far is it from Q to R? 2. So it's saying the length from here to here is 11, and the length from here to here is 9. So how big is this length? Well, you just subtract them. What if I told you that this length was 8 and this length was 4? How big is that length? 12. And we can do that with segments or with angles. So if angles or segments are next to each other and you know some of the information, then you can use addition or subtraction to figure out the rest of the information. We'll do both. Yeah. Sometimes there's not enough information in ALEKS, or I don't like the way that they set it up. So here we have a triangle. We know 2 of the angles. How do we find angle number 3? Yeah, we add up those 2. So 74 and 54 are going to make 128. And then we take 180 and subtract 128, and we get 52. Any idea why that works? Why does every single triangle add up to 180? That's a good way to look at it. If you had a rectangle or a triangle, then they add up to, well, you can put 2 triangles inside of it. So that's actually a really good way to look at it. If I have, and it's whether it's a triangle or a square, it's going to work both ways. And that adds up to 360. And if you divide that into 2 triangles, this plus this plus this plus this plus this plus this is going to add up to 360. So each triangle is going to add up to 180. There's another way to look at it. We know every straight line is 180 degrees. What if we just extend this out a little bit? And then I'm going to draw this line here. And I'm just going to slide that over. So I'm going to take this and slide it over like that. Now, this angle here matches this angle here, right? And this angle here matches this angle here. Right? So, these 3 angles make a straight line. And those angles match, and those angles match, so every single triangle adds up to 180. Now, there is a form of geometry out there where that's not true. If you were to draw a triangle on the Earth, let's say that the Earth was totally smooth, the angles on that triangle would not add up to 180. And I can prove it to you. Let's say you are on a sphere, and here's the equator. You and your friend are standing at the North Pole, and one of you walks straight south. Okay? And you're leaving footprints behind you. Well, your friend is going to go straight south, but at a 90-degree angle from you. So they're going to walk straight south. When they hit the equator, then you guys turn and walk towards each other. What do you notice? That is a triangle with 3 90-degree angles. Weird, right? So if you were to paint inside there, you would create a giant triangle on the Earth, and all 3 angles are 90 degrees, which means they add up to 270. So on the Earth, every single triangle has more than 90 degrees, or more than 180 degrees. So if you drew a regular triangle on a flat piece of paper, it would look like this. But if you draw a triangle on the Earth, it kind of bulges out a little bit. And which is kind of weird because we live on the Earth, right? There's another form of geometry, there's another figure out there where the angles actually curve in. And every triangle is less than 180. So the 180-degree rule only works on flat pieces of paper. It doesn't work on the Earth. So how many of you guys are farmers or ranchers? You got a farm? Guess what? Your fields are not rectangles. You think they are, right? You think that you have a field with 4 right angles, and this side are the same length, and this side and this side are the same length. Not true. Watch this. You kind of can, but nobody does. I'll show you what I mean. All right, this is pretty cool. Okay, you think your fields are rectangles, kind of like Colorado and Wyoming. So I guess I can do that from over here. So this is a right angle, and this is a right angle, and this is a right angle, and that's a right angle, right? And this side is equal to that side, but the top is not the same length as the bottom, right? Let me show you. I'll show you how to do that. So there are a couple of things to look at here. First, let's measure how far is it from here to here. Yeah. So 362, right? Well, let's measure from here to here. 337. So is Wyoming a rectangle? No, it's not. Yeah. So could you force your field to be like that? Sort of. Yeah. Watch what happens when we try to do that. That is a really good question. So let's zoom out a little bit. So the problem is the left side and the right side of Wyoming are straight lines, meaning if you were just to walk, it would look like a straight line. The problem here is the bottom and the top of Wyoming are actually not straight lines. And you might not believe me, so let's... Okay, so on most flat maps, the top of the United States is straight, right? But this is a globe. So watch this. When I measure from here to here, it's not a straight line. So the lines on the Earth, the longitudinal lines that go from North Pole to South Pole, they are straight lines. If you were to walk along them, you would do a perfectly straight path. But the latitude lines, the ones that go around sideways, only the equator is a straight line, which means if you were to walk from Vancouver to Minnesota along that line, you would have to take a big step with your right foot and a smaller step with your left foot because you'd have to curve. So you'd have to curve to go along this. If you walked a straight line, it would look like that one that I just measured. we could have done it that way, but then the GPS coordinates would have been really weird. It would have really messed things up. So if you wanted to build a fence along the top of Wyoming, it wouldn't be a straight fence. It would have a very gentle curve to it. So could you force your field to have 4 right angles and 4 straight sides? Something's got to give. If it has 4 equal sides, then one or more of the angles won't be 90 degrees. If you force all the angles to be 90 degrees, then one or more of the sides will either be the wrong length or it won't be a straight line. Now, you can actually see where this creates problems. So when you try to draw a bunch of rectangles on a round earth, then weird things happen. So let's look at this. This is not working very well. There we go. All right. So a long time ago, we created the Four Corners Monument, right? And this was before GPS, and they got it pretty close. This is hard to, maybe I should just go over to my computer. So look at that. The Four Corners Monument is exactly, that little medallion right there is exactly where it's supposed to be. Except they were off by a little bit. When they got GPS going, they realized that they missed. Now, they were just doing this by hand before, and they got pretty close. So you can see up here, they had to kind of move the line a little bit. So right there. So this line was coming down, and it didn't run right through, so they had to change this line. And they had to move. Congress said that medallion is the center of those states. So Utah got a little bit more territory, and Colorado got a little bit less. Let me hold on a second. Let me. Well, that's because the terrain is on. If I turn this off. Yeah. Yeah, see, that's where they messed it up. Now, if you look, I don't know if I'll be able to find this in a hurry. Anyway, the side of Utah is not totally straight. There are some more corrections in there because everybody wants their field to be a rectangle, right? But you can't really draw a rectangle, so not here. Let's look here. Okay, so they wanted to go through and draw nice squares everywhere, right? But we just learned that you can't really draw squares. So we end up with a lot of stuff that looks like this. See how the squares don't quite line up? So somebody has to give. So they altered this square a little bit to make it work. Look how these aren't even the right shape at all. And that's what happens when you try to draw squares on a globe. So if we come down and look at Emery County. So look at this. They have to sort of fudge the edges to make it work. Those are those are the state squares. So when Utah was made a state, so these are called, okay, let me see. I can't remember. These are called sections, and these are called townships, and these are called sections. So these are 1 mile by 1 mile by 1 mile. So these are 6 miles by 6 miles. So there are 36 little squares inside of this, and 4 of the squares were given to the state. So the yellow is what the federal government owns, and the blue is what the state owns, and then this is Forest Service, white is private. And this land is owned by the state, and it funds the schools. So, yeah, right here. So all of this land, as you go to Price, with all of the gas wells on it, it's all blue. So what happened is the federal government said purple is national park. So there used to be all of these yellow squares inside here, or blue squares. And the federal government said, we want that land, and we will trade you for this land. That's Indian reservation. So the federal government said, we will give you all of this land if you will give us all of the blue squares inside there. And then Utah either sells that land or leases it or charges companies to mine coal and gas. And then that money goes into a big, huge pot, and then it's distributed to the schools. So Emory High gets like $150,000 a year from this fund. So anyway, but you can see you can't draw squares or rectangles on a globe. It just doesn't work. It messes everything up. So your field is not what you think. And then look at this side of Utah. So they lined it up for a while, and then it had to jog over. And then that happened actually in Emory County too. So if you look at a map of Emory County, it's not, oh, right there. Yep. There's one, and then there's a smaller one. I don't know if you can see it, but there's a little one right there. So it just creates problems trying to draw rectangles and stuff from there. Okay. No, like I said, something's got to give because you're trying to force a flat object onto a round. Either you make all the sides the same length and then the angles don't work, or you make all the angles 90 degrees and then the sides don't work. So it's not possible. You can sort of make it close, but something's got to give. No, can't be done. Can't be done. I don't. Okay, so moving on. Do you remember how to graph slope-intercept form? Y equals 2x minus 7. So this is your y-intercept. So we put -7 on the graph, and then that is the slope. And don't forget, slope is rise over run. How do you remember that? If you want to go snowboarding, you have to rise before you can go down the run. Right? So we would put up to over 1, and then we just draw the line. Good. -2x would be down to over 1. What if it was like -2/3? Down to over 3. Which way is over? Always to the right. We always go over to the right. Good. The graph will always fit in the screen that they give you. Well, you might have to go backwards. Like if it said 4x plus 8, and you started there, and you wanted to go up 4 over 1, obviously you can't. So you just have to go backwards, down 4, left 1, like that. Yeah. Yep. It doesn't actually care which points you graph. All it cares about is that the line is in the right place. I don't know. You can just do the line. I know it doesn't grade the dots, so you probably just do the line. Right here is a line, or a line segment we call JL. How do you find the midpoint? You could count. What if you don't want to count? How would you find the midpoint? Take the average. How do you take an average? Add the two numbers together and divide by 2. So 10 plus negative 4 would be 6. 6 divided by 2 is 3. The location of the midpoint is 3. Parallel and perpendicular lines. What does it mean to be parallel? They don't cross. They're the same distance apart. Perpendicular. They cross at a 90-degree angle. Good. Angle addition. If 1 is 72 and QPS is 146, how would we find angle 2? Would be through subtraction. 146 minus 77. Yep. What if it told me 1 and it told me 2 and it wanted me to find the big angle? Then you'd add them together. All right. Angle 2 is 99. Find all of the other angles. 4 is going to be 99. What do we call angles that are in that orientation? Starts with a V. Vertical angles. Yep. Okay, how would we find angle 1? 180 minus 99 is going to be 81. And if angle 1 is 81, then 3 is also 81. Good job. Okay. What does it mean to be an acute triangle? Yeah, acute means less than 90, but if I had a triangle, how do I know that it's acute? Close. Triangle C, they're all acute. In order for a triangle to be an acute triangle, all 3 angles have to be acute. Yes, a right triangle has to have 1 right angle, and an obtuse has to have 1 obtuse. Why not 2 obtuse? It would break the 180-degree rule, right? So you cannot make a triangle with 2 obtuse angles unless you draw it on a sphere. But on a flat piece of paper, it can't be done. Okay. Simplifying square roots. Sometimes you can. So we're going to factor this. 2 times 9, 3 times 3. And then we circle pairs, not the fruit. We circle pairs. And for every pair, what do? We bring one out front. So for that, I'm going to bring a 3 out front. And then what stayed behind? So, well, the 9 factored, so we ignore the 18 and we ignore the 9. We only look at the end of the line. What? No, that'll mess it up. Because 18 is made up of 2 times 3 times 3. So if you said 18 is made up of 2 times 3 times 3 times 9, that's going to mess it up. So let's look at 24, root 24. That is 6 times 4, 3 times 2, 2 times 2. What can we bring out? Set of 2's. So what's my answer? 2 root what did not come out? Which makes 6. 3 times 2. Yeah. So again, we ignore those. Okay. What about 150? And that would be 10 and 15. Oh wait, that's not what I wanted. Let's do 200. So 10 and 20, 5 and 2, 5 and 4, 2 and 2. So I delete those. What can I bring out? A set of 2's and a set of 5's. So what do we write in the front? A 10. 2 times 5. So 10. What did not come out? Just the 2. Now, hopefully you've seen that before, but I highly doubt that your teacher taught you why that works. I'm going to teach it to you, and you're going to say, oh my goodness, that makes so much sense now. Why do we simplify this way? Well, first, if we had a problem and the answer to the problem was 1/2, how many different ways are there to write a fraction that's equivalent to 1/2? Can you think of another fraction that's equal to 1/2? 2/4. What else? 4/8. How many are there? A lot. In fact, an infinite number. So to make our lives easier and to guarantee that everybody ends up with the same value, we say anytime you have a fraction, simplify it. Okay? Well, the same sort of idea applies to square roots. There are a lot of different ways to write square roots that are equivalent to these square roots. So one of the rules that we've agreed upon is simplify all square roots. And there are other rules that we'll run into later. But for now, that's the one that we're dealing with. And so to guarantee that everybody comes up with the same value, this is the method for simplification. Now, there are a series of numbers that you can simplify the square root and you don't end up with a square root. Can you think of a number I can take the square root of and get a non-square root answer? What number can you square root and get a whole number? No, the square root of 2 is the square root of 2. Can I put a number in there and get a whole number as an answer? Some of them are odd. Yeah. What number can I square root and get a whole number? How about 9? What happens when you square root 9? You get 3. Are there other numbers like that? What are they? 11 isn't one of them. 16 is, though. 64, and there's actually a whole series of those numbers. 1, 4, 9, 16, 25. What would the next one be? 36. How'd you get that? Yeah. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. So 36, 49, 64, and so on. Those numbers are called perfect squares. Okay? And anytime you take the square root of a perfect square, you get a whole number. So, how do we simplify square roots? We break the square root into a perfect square and then everything that's left. Is there a perfect square inside of 18? Do any of those numbers in this list go into 18? 9. And 18 is 9 times 2. So the square root of 18 is essentially just the square root of 9 times the square root of 2. Do you see it? Tristan? So how do we simplify this? We just square root the 9. And I get that answer. 3 root 2. Okay? Look at the square root of 24. Does 24 have any perfect squares inside it? Four. And 24 is the square root of 4 times the square root of 6. And the square root of 4 is 2. So 2 root 6. Okay? Does 200 have any perfect squares in it? 4. Does 4 go into 200? Yes. 25. Does 25 go into 200? Yes, but there's a bigger one. No, 64 doesn't work. No. 100. Right? So root 200 is really root 100 times root 2. And root 100 is 10. So the answer is 10 root 2. So if you remember that, you can simplify these in your head. So what is the square root of 75? Does 75 have any perfect squares inside of it? 25. So the square root of 25 is 5. And what's left? 25 times what is 75? If you had quarters, how many quarters are 75 cents? Would be 3. Okay. What about the square root of 72? 36. Yep. So the square root of 36 times the square root of 2. So that simplifies to be 6 root 2. What about, let's do the square root of 90. Is there a perfect square that goes into 90? 30 is not a perfect square. So let's go through them. First one is 4. Does 4 go into 90? No. 9. Right? 4, 9, 16, 25, 36. So that is the square root of 9 times the square root of 10. So the answer would be 3 root 10. So I want you to log into Alex, go into Module 1, and you'll probably have a bunch of these topics passed off already. And we're just going to work on the first half today. So go in and start that, and then tomorrow we will do the second half.